Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good day to everyone. For this week, we will be discussing on chapter 10 on the characteristics, processing and applications of polymers. Before we begin with the presentation, let us look at the outlines of the chapter, which is first on the types of polymers, followed by crystallization, melting and glass transition phenomena in polymers. We will also discuss on the polymer processing and lastly on the applications of polymers. These slides are prepared and presented by myself. I am Dr. Siti Haja Sheikh Muhammad Fazullah from Faculty Kejuruteraan Mechanical UTM. The LO, the learning objectives of this particular chapter is first to describe a typical polymer molecule in terms of its chain structure and repeat units. Second is to calculate number average and weight average molecular weight and the degree of polymerization for a specified polymer. The third LO for the chapter is to cite the differences in physical and mechanical characteristics of thermoplastics, thermosetting polymers as well as elastomers. And lastly, for students to be able to name and briefly describe the polymer processing methods and its applications. These are some of the issues that we will try to address in the chapter. The first one is on what are the general structural and chemical characteristics of polymer molecules? What are some of the common polymeric materials and how do they differ chemically? The third question could be how is the crystalline state in polymers different from that in metals and ceramics? And what are the tensile properties of polymers and how are they affected by basic microstructural features? And lastly, what are the primary polymer processing methods? Correlation with the previous chapters that is related to polymers is in terms of the classification of materials. This would have already been introduced to you at the beginning of the course, whereby we know that there are three main classes of materials, which are metals, polymers, and ceramics, besides the fourth one, which is composites. And this was briefly introduced and discussed in chapter 1 with some of the prominent features or characteristics of each type. And the reason why they behave differently is further elaborated when we discuss on the atomic bonding and structure of materials. And we know from chapter 2 that polymer materials probably have covalent bonding between the molecules. And one of the important example given is for methane molecule, whereby we have this carbon atom at the center here with four other hydrogen atoms, and they signify how they are positioned. And this material is said and discussed to be having single bond and non-polar. The first part of this chapter is on the types, classifications, and structure of polymers. Now, let's first define what is a polymer. So polymer is defined as a material that is made of long molecule chains, or called macromolecules, which consist of many repeat units called the mers. An example is given here for ethylene, as in polyethylene. The basic unit or the monomer here is the ethylene, and it is repeated in this long chain of polyethylene. Similarly, we are seeing other examples for polyvinyl chloride and polypropylene. So what is so close to us if we look at our body? We know that our blood cell, our genetics, they are related to DNA of a human being. And this DNA is actually made up of proteins, which is also under the categories of polymers. So here is a GIF image, live image of DNA and how it looks like. And on top here is other examples of what a polymer chain might look like in 3D. So if we are to look at history, when was polymer first introduced? If we look at history, it has already been used largely in the old days, and they are called ancient polymers. So originally, natural polymers were used, especially those from wood, rubber, cotton, wool, leather, and silk. And among the oldest known uses of polymers are the rubber balls, which was used by Incas, and Noah. If you remember about Noah's Ark, right? As in Nabi Noah, right? Noah used pitch, which is a natural polymer, for his ark untuk bahtera. So these are some of the images that we can relate to ancient polymers or polymers that are produced by God. Now, let's first talk on the structure or the structural aspect of polymers. Before we talk about the classification, let's just touch lightly on the molecular structure for polymers. There are basically four types of molecular structures for polymers. The first one is linear. Second is branch, as you can clearly see here. Third is cross-linked polymer. And lastly, the network polymers. And we can relate some of the examples for each. For a linear type of polymer, we're talking about the high-density polyethylene, which is from the PE group, the PVC itself, the polystyrene, the polymethyl methacrylate, and nylon. For branch polymer, we're talking about low-density polyethylene. For cross-linked polymer, example is vulcanized rubber or elastomer. And for network, we're talking about thermoset materials like epoxies, polyurethanes, and phenol formaldehyde. Now, let's introduce you to the classification, the basic classes of polymers. There are basically two types of polymers in terms of this classification approach. The first one is called plastics, and the second one is called elastomer or rubber. Plastics are further divided into thermoplastic and thermoset. Thermoplastics include those that are crystalline in structure and those that are non-crystalline or called the amorphous material. So the classification of polymers include the thermoplastic, thermoset, and elastomer. And thermoplastic composed of long chains produced by joining together the monomers, and they typically behave in a ductile manner. So the chains may and may not have branches, which is either linear or branch polymers, which you have observed in the previous slides on the molecular structure of polymers, and you can now relate it to this. So this type of material will soften and melt when heated and solidify upon cooling, and thermoplastic can be recycled easily. The second type of polymer material, which is the thermoset, composed of long chains, either linear or branch, of molecules that can strongly cross-link to one another to form 3D network structures. You have also seen the type of molecular structure for this network structure. And they are typically stronger but brittle compared to the thermoplastic material. And upon heating, thermoset material do not melt, but they decompose. And because of this, it is hard to recycle the thermoset materials once they cross-link. And the third major classes of polymer is called elastomer, or more commonly known as rubber. They have an elastic deformation greater than 200%, and this may be thermoplastic or lightly cross-linked thermosets. And they consist of coil-like molecules or polymer chains, which we will talk in more detail later on, and they can reversibly stretch once force applied. And so, because of that, they are highly elastic material. The polymer composition and structures, we can see that most polymers are hydrocarbons, which means they are made up of carbon and hydrogen atoms. And each of the four valence electrons of carbon atoms are covalently bonded to either hydrogen, atom or the adjacent carbon atom, and the covalent bonds between each molecule is strong, but having weak van der Waals or hydrogen between the macromolecules. An example of the structure is the saturated hydrocarbon, whereby each carbon atom is singly bonded to four other atoms. Example given here is the structure of ethane with C2H6 atomic structure. As you can see on this slide, we have examples of the composition and molecular structures for some of the paraffin compounds with this generic molecular structure of C2H2N plus 2. For methane, it has one carbon atom with four hydrogen atoms with a basic unit like this and boiling point of -164 degrees C. This is followed by ethane with C2H6, which was already previously discussed, having a saturated bond between them with single bonding, and propene is C3H8, butane C4H10, pentane is C5H12, and hexane is C6H14. We can also observe that the boiling point is increasing from -164 up to 69 degrees C for hexane, and these are some of the simple hydrocarbon from the paraffin family. We have taken a look at the saturated hydrocarbon condition. What about the unsaturated ones? So when we talk about unsaturated hydrocarbon, we are seeing not the single bond between the carbon atoms, but either double or triple. Double and triple bonds are somewhat unstable and can form new bonds. So example given here is the double bond found in ethylene or ethene, which is C2H4, shown here, and the triple bond found in acetylene or ethene with C2H2, diagram shown on the down here. Now, let us discuss on the chemistry and structure of polymer. An actual polymer, if you can imagine, is gigantic. That means it's magnificent. It's huge molecules compared to a hydrocarbon molecule that we have just discussed briefly. The atoms are bonded together through covalent bonding, and a string of carbon atoms form the backbone of the molecule chain, and each carbon atom bonds to two adjacent or neighboring atoms. The two remaining valence electrons for each atoms are involved in the side bonding with either atoms or radicals, and they are positioned close to the chain. So down here is an example of polyethylene molecular structure, which is a long chain of hydrocarbon. Paraffin wax for candles is a type of a short polyethylene. For bulk or commodity polymers, in table 14.3 here, we are given examples of a list of repeat units for 10 of the more common polymer materials, which include polyethylene, PVC or polyvinyl chloride, polytetrafluoroethylene or PTFE, polypropylene, polystyrene or PS, polymethyl methacrylate, phenol formaldehyde or bakelite, polyhexamethylene avdipamide or nylon 66, polyethylene terephthalate or PET, which is a type of polyester, and polycarbonates. So from the past few tables here, what you can see is that the repeat unit is different for each type of these commodity polymers. Now that we have learned on the very basic introductory part of polymer, the structure, the definition, as well as the classification, let's look at the first sample problem for the chapter. As an example, how would you define the word polymer? And B, how do you compare the main differences between thermoplastic and thermoset polymers in terms of their polymer chain structure, and how do they respond to heat? Let's now look at the solution. Polymer is defined as material that is made of long molecule chain or macromolecules which consist of many repeat units called the mers. And the main differences between the thermoplastic and thermoset polymers in terms of the polymer chain structure and the response to heat are given in this table. In terms of the polymer chain structure, we are now aware that thermoplastic material composed of long chains that may or may not have branches. Contrary to that, the thermoset material have a polymer chain structure whereby the long chains that are cross-linked to one another to form 3D network structures exist. And in terms of the response to heat, the major difference is that the thermoplastic material, because of the molecular structure, it can be reversibly cooled and reheated. Therefore, they melt when reheated and harden upon cooling. Contrary to that, for the thermoset material, they cannot be reversibly cooled and reheated because of the 3D network structures. Therefore, once they form a molecular network through chemical reaction, they don't melt when reheated, but instead they degrade. Now, let us now have a brief look at the synthesis of polymers. Basically, there are two types of polymerization. Number one is called the addition or chain polymerizations. So what it is that it is sometimes called the chain reaction polymerization. It is a process by joining monomers, one at a time in chain-like fashion to form a linear macromolecule. Resultant repeat units have the same formula as the reactant monomers, and it happened under appropriate heat, pressure, and catalyst. And the carbon atom become active and they joined with other mers to produce the polymer chain. And the process continues until termination. One of the examples for this type of synthesis of polymers is for the formation of polyethylene from ethylene gas. Before we look at the illustration of the addition polymerization, or what we call the chain polymerization, now, points to ponder. How are the gigantic molecules of polymers produced from mer? Would you now be able to self-assess yourself and answer the question? Right. Going back to the discussion on the addition or chain polymerization, at the initiation stage, we have this radical unit with this structure here, and they combine together through addition. They call the second step to be propagation. And then at the end of the process of addition or chain polymerization, we have the termination. So we can have this proportionation or combination. Second type of synthesis of polymers is called the condensation or step polymerization. This is the formation of polymers by stepwise intermolecular chemical reactions that may involve more than one monomer species, and there is usually a small molecular weight byproduct such as water that is eliminated or condensed. Therefore, we have the word condensation here. The resultant repeat units do not have similar formula as the reactant monomers. For example, formation of polyester PET from ethylene glycol and terephthalic acid. So we can illustrate the condensation or step polymerization process through this example. This is to produce nylon 6,6 from the condensation of hexamethylene diamine and adipic acid, where we release the water molecule. Now, We are still discussing on the structure of polymer, and now we are looking at the characterization where we can calculate for the molecular weight and also the degree of polymerization. First, let's understand about the molecular weight, capital M, which is the mass of a mole of chain. Imagine if we have a short chain and a long chain. The short chain polymer molecules will have low molecular weight, and as expected, the longer polymer molecule chains definitely have high molecular weight. But not all chains in a polymers are of the same length. Therefore, there is a distribution of molecular weights. So in order to quantify this, we may be using statistical approach. From statistical approach, as I mentioned, we can now calculate for the molecular weight distribution. If we look at this particular plot of the amount of polymer versus the molecular weight, we can define two things here, which is the average molecular weight based on the weight average or the number average molecular weight using the two formulation. So this small letter n refers to the number average molecular weight, and this small letter w refers to the weight average molecular weight. And this xi is the number fraction of chains in the size range I, and small letter wi is the weight fraction of chains in size range I. Now, let's look at the sample problem 2 in this chapter on the calculation of average mass of a class. If we have 10 students with different weight or mass in pound, what is the average weight of students in this class? A, based on the number fraction of students in each mass range, and B, based on the weight fraction of students in each mass range. So before we can answer the question, we need to further characterize and divide the range of weight for the 10 students into different classes. It is shown in this slide. So the solution begins with the first step, that is to sort the students into weight range. Based on the data given, we can use 40-pound ranges and we can produce this kind of table. So from the data that we can have a range from 81 to 120 pound, 121 to 160 pound, 161 to 200, 201 to 240, 241 to 280, 281 to 320, 321 to 360, and 361 to 400. And the number of students are as given on the table based on the data given in the original question. And from there, we can calculate for the weight mean or small letter wi. So now, because it is already calculated and tabulated in the table, we can calculate for the summation of ni, which is the number of students, that is 10, and the total of this number of students times the mean weight, which is summation of ni wi, and this equals to a total of this 1881. Now, if you're not sure how we can calculate the number of fraction of students, xi is actually ni divided by summation of ni. In this case, it's 10. And wi, the weight fraction of students, is calculated as ni wi, which is a combination of these two information, and this is divided by the summation of all. So as an example, for the first range of 81 to 120 pound, x at 81 to 120 equals to ni, which is 2, divided by summation of ni, which is 10, and that equals 0.2. And the weight fraction at this range is 2 times wi, which is 110, divided by summation of these two. Now it becomes 0.117. So we can now calculate for the whole of this number fraction and weight fraction. So based on that information, we can now calculate for the number average and weight average of the molecular, in this case, the weight range of the class, and this Mn, the average molecular number, is given by 188 pound, whereas the molecular weight average is given by 218 pound. Next to that, we can also quantify the degree of polymerization, and it is actually an indication of the average number of repeat units per molecular chain. So, from this example here, the degree of polymerization is 6. And how do you get that? This is based on this formulation here, which is the number average divided by average molecular weight of repeat unit for copolymers, which is calculated as the summation of the chain fractions times the molecular weight of repeat unit I. Now, let's look at sample problem 10.3. It is a combination of question on the average molecular weight and the degree of polymerization. If the resolution is small for you, you can also refer to the e-book chapter from the Callister textbook on example problem 14.1 in chapter 14. So, on the computations of average molecular weight and degree of polymerization, we have to assume that the molecular weight distribution shown in figure 14.3 is for PVC. And for this material, we want to compute the number average molecular weight and the degree of polymerization as well as the weight average molecular weight. So we need to recall the equations for each one of these. So A is to solve for the number average molecular weight. So this will be the formula that we'll be referring to. So the data necessary for this computation is presented in table 14.4a. Now that we have the molecular weight range and the mean, we can now calculate for the fraction and then we can get a summation. So according to equation 14.5a, summation of the XIMI products yields the number average molecular weight, which is, in this example, 21,150 gram per mole. And for B, to determine the degree of polymerization, we use equation 14.6 from chapter 14 of the book. So it is first necessary to compute the repeat unit molecular weight. For PVC, each repeat unit consists of 2 carbon atoms, 3 hydrogen atoms, and a single chlorine atom. So by referring to table 14.3, which we have discussed previously. Furthermore, the atomic weight of carbon, hydrogen, and chlorine is given as such. Therefore, we can calculate M to be 2 times 12.01 gram per mole for carbon, 3 times 1.01 gram per mole for hydrogen, and 35.45 gram per mole for chlorine, and it becomes 62.5450 gram per mole. Therefore, the degree of polymerization is calculated as 21,150 divided by M, and that is 338. For question C, using table 14.4b, we need to calculate for the weight average molecular weight. So before we can do that, we need to calculate for Wi, or the weight fraction, and before that the mean from this molecular weight range from 5,000 to 40,000. So the sum of this equals 23,200, which is the average molecular weight of this PVC. Another sample problem is given on this question on the slide. A commercial grade of PVC polymer with a linear formula of C2H3ClN is produced using chain polymerization process. Molecular weight data of the polymer is given here. How do we compute the number average molecular weight, the weight average molecular weight, and the degree of polymerization. So this example is using a different unit for the atomic mass. Carbon 12.011 U, hydrogen 1.008 U, and chlorine 35.45 U. For the molecular weight data for the PVC, we are given this data here. So in terms of the solution, we need to solve for the number fraction and the weight fraction. From there, we can calculate the number average molecular weight, which is a summation of xi, mi, and that equals to 41,300 gram per mole, whereas the weight average molecular weight is given by summation of wi, mi, and that is 45,300 gram per mole. For the degree of polymerization, from the given information, dP equals to the number average molecular weight divided by m, and that equals to 660.84. We're still discussing on the structure of polymers, and we must be aware that the copolymers is where two or more monomers are polymerized together. They can have either random configuration, alternating configuration, block, or graft. As you can see on the illustration given here, random is where these atoms of A and B are randomly positioned along the molecular chain, whereas for the alternating, this is where A and B are alternately positioned in the polymer chain. For the block type of copolymers, we can have large blocks of A units, which is alternating with the large blocks of B unit. And lastly, for graft, they have like a branch here, whereby the chains of B units are grafted onto the A backbone.